Hello friends, welcome back to my YouTube channel. Welcome to my discussion on adsorption. This is part number 7 of that discussion. I will continue discussing adsorption isotherms, and this time I will be discussing the Gibbs adsorption isotherm. In part number 6, I had discussed Brunner, Emmett, Taylor, that is BET adsorption isotherm. In part number 5, I had discussed the Lamour adsorption isotherm. I am giving link to the entire playlist of my videos on adsorption. You please, if you have not seen those videos, you please watch those videos. So let us begin today's discussion. Okay, so let us begin by understanding how to represent the adsorption equilibria. So whenever you have the two phases are involved in adsorption. One is the adsorbent, which is a solid, and it is contacted with a fluid phase. It could be a gaseous mixture or a liquid solution. And then one or more component from the fluid phase, it gets differentially concentrated on the surface of the adsorbent. This is what happens during adsorption. So you have a fluid phase that is in contact with the adsorbent phase. That means fluid phase, it is in contact with the adsorbent phase, and adsorbent phase is solid phase. So after sufficiently long time, what will happen? An equilibrium will reach between the fluid phase and the solid phase. And when this happens, when an equilibrium is reached, three parameters are important, or three parameters are involved. So at equilibrium, there are three parameters that are involved. And which are these three parameters? One is the concentration of the adsorbent in the fluid phase, which we will denote as Ca in our discussion. So we are talking about concentration in the fluid phase, and that concentration we are going to denote by Ca. And then the second parameter is concentration of the adsorbent on the surface of the adsorbent. So once the component gets adsorbed on the surface of the adsorbent, we are going to denote its concentration on the surface by Cs. So this is this other parameter. And the third one is the temperature, that is T. So you have three parameters. Whenever an equilibrium is reached between fluid phase and the solid phase during adsorption, three parameters can be used to represent the equilibrium. You can use these three parameters to represent the equilibrium. So the capacity of an adsorbent, let me first erase it so that you'll understand. The capacity of any adsorbent to adsorb a particular component, it depends on how these three parameters interact with each other. The capacity of an adsorbent, it depends on these three parameters and how they interact or how they are dependent on each other. Now, as I said, to study the equilibrium, you can study the equilibrium with the help of these parameters, but you can make your job easy. How? You can keep one parameter constant while you can vary the other two. That is, out of this three, Ca, Cs and T, one parameter can be kept constant, and then other two can be varied, and you can then study how equilibrium is reached by varying those two parameters. So one parameter can be kept constant while the other two can be varied. So in this way, you have three different ways of representing the concentration. So accordingly, there are three different ways to represent equilibrium. The first way is you can change Ca and Cs and get these values. And once you have these values, you can plot them against each other by keeping T constant. So Ca is plotted against Cs by keeping T constant. This is one way. Then the other way of representing the equilibrium is Ca is plotted against T by keeping Cs constant. And the third way is Cs is plotted against E by keeping Ca constant. So I have discussed about this representation in my earlier one of my earlier videos. I have given link to the entire playlist. You please watch that. So the idea is, out of the three parameters, you keep one parameter constant and vary the other two, and then study how equilibrium is reached. So once you get the equilibrium data, you can plot it in three different ways. So one parameter is kept constant, that is, you can keep T constant, then you can keep Cs constant, or you can keep Ca constant. Cs is concentration of the adsorbate on the surface of the adsorbent, and Ca is concentration of the adsorbate in the fluid phase. Now, in our discussion, we are talking about the first way of representing the equilibrium. That is how Ca changes with Cs when at constant temperature, and the curve that you get by plotting Ca against Cs at constant temperature, that curve is called the adsorption isotherm, and that is what I am discussing in this particular video. So let us move ahead. Now let us talk about adsorption isotherms. So as I said, if you plot Ca against Cs by keeping T constant, Ca is plotted against Cs by keeping T constant. That is, on the y-axis you are plotting Ca, and on the x-axis you are plotting Cs, and you get the curve, and this curve is called the adsorption isotherm. The resulting curve, it is called the adsorption isotherm. So this is the adsorption isotherm. What you can note for adsorption isotherms, this particular way of representing the equilibria, adsorption equilibria, this is the commonest way of representing equilibria. So adsorption isotherms they are the commonest means of representing adsorption equilibria, the commonest way of representing the adsorption equilibria. So you can note an adsorbate, a particular adsorbate will give different adsorption isotherms on different adsorbents. So for example, if you are talking about adsorption of A, that is adsorption of A, and if this is the curve that is obtained on adsorbent number 1, so on some other adsorbent will get a different curve, different adsorption isotherm. So you will get this on some other adsorbent, let us say adsorbent number 2. So the point is, an adsorbate will give different adsorption isotherms on different adsorbents, and different adsorbates will give different adsorption isotherms on the same adsorbate. So for example, if you have, let us say, let me erase it so that I can explain. So for example, let us say that we have got this adsorption isotherm for adsorption of B, adsorption of A on an adsorbent, let us say adsorbent X. Now, if I keep this same adsorbent and study adsorption of some other component, let us say B. So A on X, and now I am studying B on X. So in that case also, or in that case, I'll be getting a different adsorption isotherm. I'll be getting, so if this is for A, this is for B. A on X, and this is B on works. So I hope you are understanding these 2 points. An adsorbent will give, an adsorbate will give different adsorption isotherms on different adsorbents, and different adsorbates will give different adsorption isotherms on the same adsorbent. So I hope this is clear to you. So let us move ahead. Now let us talk about various adsorption isotherms. The first one is the simplest adsorption isotherm. I have discussed it in one of my earlier videos. Link to the entire playlist is available in the description section. The simplest adsorption isotherm is applicable, even though it is simple, but it is applicable when adsorption occurs by simple mechanisms. And such simple mechanisms are associated with very few systems. So very few adsorption systems will be having simple mechanism. So simplest adsorption isotherm you can use, but it is applicable when adsorption occurs by simple mechanisms, and very few systems are simple. Then let me list some commonly used adsorption isotherms. You have the Langmuir adsorption isotherm. Then you have the Brunner-Emmett-Tiller, that is BET adsorption isotherm. And then you have Gibbs adsorption isotherm. Out of this, I have discussed the first 2. And today, in this video, I'm talking about the Gibbs adsorption isotherm. So, as far as these 3 isotherms are concerned, all these 3, they are based on some theories that have been proposed in literature to explain the phenomenon of adsorption. So, these 3 adsorption isotherms, they are based on theories. They are applicable to adsorption of gases, that is adsorption of a component from a gaseous mixture. For that application on these adsorption isotherms can be used. And the other thing is, none is applicable universally. You cannot apply any of these 3 adsorption isotherm universally. That means to all the cases of adsorption. One adsorption isotherm may work nicely with one scenario. It may not work nicely with the other scenario. So that is the meaning of this statement. None is applicable universally. Then you have the Freundlich adsorption isotherm. Why it is written separately out of this 3? You have a group of the 3 adsorption isotherms, and I have noted down Freundlich adsorption isotherm separately. What is the reason? It will come to me. So this Freundlich adsorption isotherm, the first difference is it is not based on any adsorption theory, while the previous 3, they are based on some adsorption theories. The Freundlich adsorption isotherm, it is not based on any adsorption theory. It is applicable to the adsorption of liquids. So first, these 3 are used mostly for adsorption of gases, whereas the Freundlich adsorption isotherm, it is mostly used for adsorption of liquids. Then it is applicable over a small concentration range. Again, this could be one of its limitation. Then the other limitation is it is applicable for dilute solutions. So we will understand it in detail I will be discussing it in detail. I will be discussing this in detail in my next video, the Freundlich adsorption isotherm. Today, I am going to talk about the Gibbs adsorption isotherm. So let us start our discussion on the Gibbs adsorption isotherm. It is based on some assumptions. Which are these assumptions? Let me tell you. So it is based on the following assumptions. The layer of adsorbed molecules behave like a liquid film. The first assumption that is made in this case is that once the gas molecules go on to the surface of the adsorbent, they behave like a liquid film. I have a schematic diagram I will show you shortly. So the first assumption is the layer of the adsorbed molecules behave like a liquid film. So based on this assumption, what is the use of this assumption? With this assumption, you can use equation of classical thermodynamics for getting the equation for Gibbs adsorption isotherm. So the first assumption is layer of adsorbed molecules, they behave like a liquid film, and due to this assumption you can use equations of classical thermodynamics in this case. The second assumption is the adsorbed molecules are free to move on the surface of the adsorbent. In the case of Langmuir adsorption isotherm and also in the case of BET adsorption isotherm, the adsorbed molecules were occupying fixed sites on the surface of the adsorbent. They were not able to move once they were on the surface of the adsorbent. But in this case, it is assumed that the adsorbed molecules are free to move on the surface of the adsorbent. So these two assumptions we are going to consider or we are going to use while deriving equation for the Gibbs adsorption isotherm. The first assumption is the layer of the adsorbed molecules, it behave like a liquid film. So this helps us to use equations of classical thermodynamics in our discussion. And the second assumption is the adsorbed molecules are free to move on the surface of the adsorbent. So we are going to consider a case of adsorption of a component from a gas mixture. That is, for example, we are going to consider a gas mixture of A and B from which only A is getting adsorbed. Out of A and B, only A is getting adsorbed. So this is the adsorbent, and now it is contacted with a gaseous mixture of A and B, and now A is going to get adsorbed on the surface. So A will get adsorbed on the surface, and the adsorbed layer, it will behave like a liquid film. So this adsorbed molecules, they are able to move on the surface of the adsorbent. So the adsorbed layer, it behaves like a liquid film. That is, the adsorbed molecules, they are free to move on the surface of the adsorbent. So I hope this is clear to you how adsorption is taking place in this case. So let us move on. So again, I had taken the same simple schematic diagram in my discussion. Now in this case, this is the liquid film, and we are assuming it to be forming. So we are assuming that the adsorbed molecules, they are behaving like a liquid film. So as adsorption continues, so you have the liquid film and more molecules of A, they get adsorbed on the surface. What happens? As adsorption continues, more molecules of A are added to the film. And according to J.W. Gibbs, what happens? The addition of molecules of A to the film, it decreases the surface tension of the film. Surface tension, this is a force, cohesive force at the surface of this liquid film that makes the surface of the liquid film to behave like a stretched elastic surface. So according to J.W. Gibbs, what happens? As more molecules of A gets adsorbed, that is, they get added to the film, what happens? This decreases the surface tension of the film. And due to decrease in the surface tension, there is decrease in the free energy of the liquid film. So due to decrease in the surface tension, there is decrease in the free energy of the liquid film. So as adsorption happens, more molecules of A gets added to the film. The surface tension of the film decreases, and this decreases the free energy of the liquid film. The free energy of the liquid film is the Gibbs free energy, that we call the free energy as Gibbs free energy. So basically, once a layer of adsorbed molecules is formed on the surface of the adsorbent, it behaves like a liquid film. And when more adsorption takes place, that is, more molecules of A are added to the film, the surface tension of the film decreases, which decreases the free energy, that is, Gibbs free energy of the liquid film. So this is according to J.W. Gibbs, and we are going to use this assumption or this fact. Which fact? The fact that the surface tension of the film decreases and the free energy of the film decreases. So let us move ahead. The Gibbs free energy, it depends on these parameters. It depends on temperature, it depends on pressure, it depends on number of moles of A content in the film, that is, number of moles that have adsorbed on the surface. We are going to denote that by Na. Then it also depends on the area that is available to the film. We are going to denote that area by As. So mathematically, you can represent this as G is function of T, temperature, pressure, number of moles of A, and surface area available to the film. So that is dG will be dabba G by dabba T at constant pressure, constant P Na As dt, plus dabba G by dabba P at constant T Na As dP, plus dabba G by dabba Na at constant T P As into dNa, plus dabba G by dabba As at constant temperature, pressure Na into ds. So this mathematical relationship you can express in this form. dG is equal to dabba G by dabba T at constant pressure, number of moles, area into dt, plus dabba G by dabba P at constant temperature, number of moles, area into dP, dabba G by dabba Na at constant temperature, pressure, area into dNa, dabba G by dabba S at constant temperature, pressure, number of moles of A into ds. So we will continue with this equation. Now previously we got this equation, dG is equal to dabba G by dabba T. We just now got this equation, dabba G by dabba T into dt, plus dabba G by dabba P into dP, plus dabba G by dabba Na into dNa, plus dabba G by dabba As into ds. Now at constant temperature and pressure, dt and dP will become 0. At constant temperature and pressure, this becomes 0 and this becomes 0. That means now the equation for dG is written as dG is equal to dabba G by dabba Na into dNa plus dabba G by dabba As into ds. Now in this equation, if you look at this term dabba G by dabba Na, this is nothing but mu A, which is a chemical potential of A, in the film. Mu A, dabba G by dabba Na is nothing but mu A. And what is mu A? Mu A is chemical potential of A in the film. Then dabba G by dabba As, it is gamma, which is nothing but the surface tension. Dabba G by dabba As is gamma, the surface tension of the liquid film. So in our next step, we are going to replace this differentials with mu A and gamma. So let us do that in our next step. Okay, so previously we got this equation, dG is equal to dabba G by dabba Na into dNa plus dabba G by dabba As into dAs, and dabba G by dabba Na is mu A, that is chemical potential of A in the film on the surface of the adsorbent, and dabba G by dabba As is gamma, the surface tension. So the next step I will be replacing those differentials with mu A and gamma. So therefore I will get dG is equal to mu A into dNa plus gamma into dAs, and I am calling it as equation number 1. Now the total Gibbs energy, it is given by this equation. G is equal to mu A into Na plus gamma into As. And if you have to get dg from this, dg will be obtained in this way. Dg is equal to mu A, because mu A into Na, if we have to take the differential of this, we will have to use the product rule, because both are variables. So dg is equal to mu A into dna plus Na into d mu A plus sigma into gamma into das plus as into d gamma, and I am calling it as equation number 2. So we have equation number 2, we have equation number 1 and then we have equation number 2. Both gives us dg. So the right hand sides of these two equations, they can be equated, and we are going to do that in the next step. So let us do that. So previously we got dg is equal to mu A into dna plus gamma into das, equation number 1, and then dg is equal to mu A into dna plus na into d mu A plus gamma into das plus as into d gamma, and I'm calling it as, or this was the equation, this was the second equation that we got previously. Now we are going to equate the right hand sides. So from equation 1 and 2, you get mu A into dna plus gamma into das, the right hand side of equation 1, is equal to right hand side of equation 2. That is mu A into dna plus na into d mu A plus gamma into das plus as into d gamma. So what happens? See, on this side you have mu A into dna. You also have the same term on the right hand side, so they get cancelled out. And then the other term, gamma into das, it is present on the left hand side and it is also present on the right hand side. So this will also get cancelled out. So you are left with nothing on the left hand side, that is 0. That is equal to Na into d mu A on the other side, the right hand side, plus as into d gamma. That is, as into d gamma is equal to minus Na into d mu A. So one term can be brought on this side, and we will get this equation. As into d gamma, that is equal to minus Na into d mu A. That is, d gamma is minus Na upon as into d mu A. We get equation for d gamma, and that is minus Na upon as into d mu A. So I hope the steps are clear to you. If you have any doubts, you can mention that in the comment section. Let us move ahead. Okay, so previously we got d gamma is equal to minus Na upon as into d mu A, and I'm calling it as equation number 3. Remember, mu A is chemical potential of A on the surface of the adsorbent. That is, chemical potential of A in the liquid film that we have assumed on the surface of the adsorbent. So at equilibrium, when the fluid phase or the gas phase is in equilibrium with the solid phase, which has the film, assumed film on its surface, the solid phase. So when they are in equilibrium with each other, and if you assume that the gas phase is behaving ideally, if the gas phase is assumed to be behaving ideally, then d mu A, that is chemical potential of A in the film, is equal to chemical potential of A in the gas phase. So at equilibrium, if you assume the gas phase to be behaving ideally, then this equation holds true. D mu A is equal to d mu Ag, where mu Ag is the chemical potential of A in the gas phase. Say here, mu Ag is chemical potential of A in the gas phase. So mu Ag, as I said, this is chemical potential of A in the gas phase. Okay, but we know we are using a known equation. Let me first erase it. I hope you have understood it. Now I can erase this. So it is known that d mu Ag, equation for d mu Ag is RT into d ln of PA, where PA is the partial pressure of A in the gas phase. R is the gas constant, T is temperature, and mu Ag, it is chemical potential of A in the gas phase. So what we can do, we can use this in equation number 3. That is, first we are going to replace d mu A with d mu Ag, and then d mu Ag will be replaced with RT d ln of PA. So this will give us this equation. D gamma is equal to minus Na upon As into RT into d ln of PA, and I'm calling it as equation number 4. Okay. So previously we got this equation. D gamma is equal to minus Na upon As into RT d ln of PA. Equation number 4. It was numbered as equation number 4. Now let us talk about gamma, the surface tension. What is surface tension? It is a cohesive force at the surface of a liquid film that makes it behave like a staged elastic sheet. So if you look at our scenario, you have the adsorbent, and on the surface of the adsorbent you have the molecules of A that have been adsorbed, and we are assuming that these molecules are behaving like a liquid film. So for liquid films at the surface, you have a cohesive force that makes the liquid surface or liquid film to behave like a staged elastic sheet, and that cohesive force is nothing but surface tension, gamma. Then we have another parameter which is spreading pressure, and this is capital gamma. This is lowercase gamma. This is capital case gamma. We are going to denote the spreading pressure with capital uppercase gamma. So capital gamma, you can say. What is it? This is the pressure exerted by the adsorbed molecules at the surface tending to spread the liquid film. So surface tension tends to keep the liquid film intact, but it is cohesive in nature, whereas the spreading pressure tends to spread the liquid film. So spreading pressure is the pressure exerted by the adsorbed molecules at the surface, which tends it to spread, which tends to spread the liquid film. So surface tension tends to keep it intact, whereas spreading pressure tends to spread it. That means these are acting the surface tension, small gamma, and spreading pressure, capital gamma. They are acting against each other. So thus the spreading pressure opposes the surface tension. I hope you must have understood now. An increase in the spreading pressure causes decrease in the surface tension. An increase in capital gamma causes decrease in small gamma. So therefore, you can relate this behavior by this mathematical equation. D gamma is equal to minus D small gamma is equal to minus D capital gamma, because they are acting in opposite ways. Surface tension tries to keep the liquid film intact, whereas spreading pressure tends to spread the liquid film. So that's why they are related. An increase in capital gamma, that is the spreading pressure, causes decrease in in small gamma, the surface tension. So they are related by this equation. D small gamma is equal to minus D capital gamma. I hope you are understanding it. If you have any doubt, you can mention that in the comment section. Now let us move ahead. So with this equation, when you use this in equation 4, that means we are going to replace D small gamma with minus D capital gamma. So it will be minus D capital gamma is equal to minus Na upon As into R into T into D ln of Pa. So we have replaced D small gamma with minus D capital gamma. So let us move ahead. So we just got this minus D capital gamma is equal to minus Na upon As into RT into D ln of Pa. Now this negative sign which is present on both the sides, it will be cancelled out. So it will be D gamma is equal to Na upon As into RT into D ln of Pa. Let us call it as equation number 5. Now equation number 5 is what? It is a form of an adsorption isotherm. Why it is an adsorption isotherm? Because if you look at this equation, it relates the amount adsorbed, that is Na, to the partial pressure of A in the gas phase. So partial pressure of A in the gas phase, it is related to Na. What is Na? This is moles of A that have been adsorbed on the surface of the adsorbent. So it is a form of an adsorption isotherm, equation number 5. And this equation, this adsorption isotherm, it is nothing but the Gibbs adsorption isotherm. So let me just write. So this is nothing but equation number 5. This is nothing but the Gibbs adsorption isotherm. This is Gibbs adsorption isotherm. Okay, so but in this form it is not useful. So we have to put equation number 5, that is the Gibbs adsorption isotherm, in a form that will be useful. And how is that possible? That is possible if you know equation for D capital gamma. If you know the equation for D capital gamma, and then you can replace D capital gamma in the equation, simplify the equation, and then you can put the equation in an appropriate form, which will be useful for finding out the surface area of the adsorbent, that is As. So we are going to understand that. So over here we get what is Gibbs adsorption isotherm. So this equation is the Gibbs adsorption isotherm. Now let us use equation for D capital gamma, so that equation number 5 becomes useful. So for equation number 5 to be useful, we need an equation for capital gamma. And once capital gamma is known, we have equation for capital gamma, you can easily get equation for D capital gamma. So let us do that. So for that, Harkins and Zura, this researchers, they based on an analogy between liquid films and adsorbed layers, because we have assumed that in this case the adsorbed layer is behaving like a liquid film. So based on an analogy between liquid films and adsorbed layers, these two persons proposed equation for capital gamma. And what is that equation? Capital gamma is equal to alpha 1 minus beta 1 into A. So in this case, alpha 1 and beta 1, these are constants. Whereas AM is area per molecule of the adsorbent A. Area per molecule of the adsorbent A. And we have equation for that. So AM is equal to AS. You are dividing the area AS with number of moles, and then Avogadro's number. So one Avogadro's number is number of molecules in 1 mole. So Na into Avogadro's number will give you total number of molecules, and we are dividing area by total number of molecules, and that's why AM is area per molecule of the adsorbent. So N in this case is Avogadro's number. Okay, so let us move ahead. Now we are going to use this equation so as to make equation number 5 useful. Okay, so previously we got D capital gamma is equal to Na upon As into RT dln of Pa. That was equation number 5. And capital gamma is alpha 1 minus beta 1 into Am. Am is As upon N A into capital N. So now let us use in the equation. So this is gamma is equal to alpha 1 minus beta 1 into As upon Na into capital N. And if you differentiate it, it will be D capital gamma is equal to alpha 1 is constant. So its derivation is its differential is 0. So it will be minus beta 1 As upon N, because these 3 are constant, and the differentiation of 1 upon Na is minus 1 upon Na square into Dna. So that means D gamma is B1 into As upon N square upon capital N into 1 upon Na square into Dna. This negative sign and this negative sign, it becomes positive. So you have beta 1 into As upon capital N into 1 upon Na square into Dna. Now we are going to use this in equation number 5. So it will be beta 1 into As upon N into 1 upon Na square into Dna. That is equal to Na upon As into RT into dln of Pa. Now dln of Pa, that is differential of ln of Pa is Pa in 1 upon Pa into Da. We are going to use that. So that is B1 into As upon N into 1 upon Na square into Dna. That is equal to Na upon As into RT, and differentiation of ln of Pa is 1 upon Pa into dPa. That is dPa upon Pa. I hope you are understanding this. Then in the next step, I will rearrange the equation. So it is beta 1 into A square upon RT into N into DNA upon Na cube, because we have Na on this side. So when it comes to the other side, that is left hand side, it will go to the denominator. So the term will be DNA upon Na cube. That is equal to dPa upon Pe. Only we have kept one term on the right hand side, whereas all other terms we have taken to the left hand side. Okay. So that is dPa upon Pa. Again, rearrangement. dPa upon Pa is equal to beta 1 A square divided by RT into capital N into DNA by Na cube. And this is equation number 6. Let us move ahead. So previously we got dPa upon Pa is equal to beta 1 A square upon RTN into DNA upon Na cube. That was equation number 6. Now the task is to integrate this equation. And for integrating equation number 6, we need to use some limits. What are the limits? Let us understand. So integrating equation number 6 with the following limits. One limit is conditions at which the adsorbed film becomes mobile. That is the conditions at which the layer of the molecules on the surface of the environment, it starts moving. So conditions at which the adsorbed film becomes mobile. So those conditions, let pressure be Pa1 and number of fluids on the surface be Na1. So we have one limit when Pa1 and Na1. And then the other limit is some arbitrary conditions Pa and Na. So we are going to integrate equation number 6 with these limits. So it will be integration from Pa1 to Pa dPa upon Pa. That is equal to integration from Na1 to Na beta 1 A square upon Rtn into dna upon na cube. So let us integrate it. Before we do that, we should note that beta 1, as, r, t and n, this group is constant. So it is going to get out of the integral. So it will be integration from pa1 to pa dpa upon pa, that is equal to beta 1 a square upon rt capital N into integration na1 to na dna upon na cube. And integration of dp upon pa is ln of pa, limits pa1 to pa, and integration, we will do the integration of the other side. So on the other side, you have beta 1 a square upon rt capital N integration from na1 to na dna upon na cube. So previously we got this ln of pa from pa1 to pa, that is equal to beta 1 a square upon rt capital N integration from na1 to na dna upon na cube. So that is, I will apply the limits on the left hand side. So it will be ln of pa minus ln of pa1, that is equal to beta 1 into a square upon rt capital N, and integration of 1 upon na cube is na raised to minus 2 divided by minus 2. So you must be remembering integration of n, let me just tell you, integration of x raised to m is x raised to m plus 1 upon m plus 1. So in this case, you have 1 upon na cube, that is na raised to minus 3, and integration of this, it will be na raised to minus 3 plus 1 divided by minus 3 plus 1. So that is na raised to minus 2 divided by minus 2. That is why you are getting this term. I hope you understand this. Okay, I will erase it. Okay, then next is, let us use the limits in the next step. So it will be, this is ln of a minus ln of b, ln of a upon b, the identity. So it will be ln of pa upon pa1, that is equal to minus 1 by 2 beta 1 a square upon rt capital N, and now I am using the limit. So it is 1 upon na square minus 1 upon na1 square, and if I use this negative sign, it will be ln of pa upon pa1, that is equal to 1 by 2 beta 1 a square upon rtn into the positions will get changed. So it will be 1 upon na1 square minus 1 upon na square. So that is ln of pa by pa1, that is equal to 1 by 2 beta 1 a square upon rtn, and simplifying it, I am multiplying this stuff into the bracket. So this is 1 by 2 beta 1 a square upon rtn into 1 upon na1 square minus 1 by 2 beta 1 a square upon rtn into 1 upon n square, and solve it as equation number 7. Now, what happens when Pa, what is Pa? Partial pressure of A in the gas mixture. When it becomes equal to Pa naught is vapor pressure. When Pa becomes equal to Pa naught, that is vapor pressure, what happens? Condensation will occur on the surface of adsorbent. And in that case, it will not be adsorption, it will be condensation. In order to make the equation useful, what I would like to have Pa naught in equation number 7. So in order to get Pa naught in equation number 7, what I will do? I will add one term on each side. What is that term? ln of Pa by Pa naught. So equation 7, ln of Pa by Pa1 plus I am adding the term ln of Pa upon Pa naught in order to have Pa naught in the equation to get it in a proper form. So since I am adding it on the left side, I will also have to add on the other side. So, okay, and let me explain it once again. You have equation number 7. You have understood it. Now, I just explained when PA becomes equal to PA naught, the vapor pressure, condensation occurs on the surface of the adsorbent. So, in order to have to get PA naught in equation number 7, so that it becomes useful, we are going to add one term on each side. So, it is ln of PA upon PA1 plus ln of PA upon PA naught. So, I have added PA naught, ln of PA upon PA naught on each side. So, ln of PA upon PA1 plus ln of PA upon PA naught, that is equal to 1 by 2 beta 1 A square upon RTN into 1 upon NA1 square minus 1 by 2 beta 1 T 1 on into 1 upon NA square plus ln of PA upon PA naught. Okay, so let us do it. So that is ln of PA upon PA naught is equal to 1 by 2 beta 1 A square upon RTN into 1 upon NA1 square minus 1 by 2 beta 1 into A square upon RTN into 1 upon NA square. And this term I have brought on this side. So it will be ln of PA upon PA naught minus ln of PA upon PA1. So in the next step, what will happen? Okay, previously we got this ln of PA upon PA naught, that is equal to 1 by 2 beta 1 A square upon RT capital N 1 upon NA1 square minus 1 by 2 beta 1 A square upon RT capital N 1 upon NA square plus ln of PA upon PA naught minus ln of PA upon PA. So if you look at these two terms, is ln of it is like ln of A minus ln of B. So it will be ln of A upon B. So we are going to use that identity only. So ln of PA upon PA naught is equal to 1 by 2 beta 1 A square upon RT capital N 1 upon NA1 square minus 1 by 2 beta 1 A square upon RTN into 1 upon N square plus, now I have used the logarithmic identity. So this is ln of PA by PA naught upon PA upon PA1. So that is ln of PA upon PA naught was equal to 1 by 2 beta 1 A square upon RTN 1 upon NA1 square minus 1 by 2 beta 1 A square upon RTN 1 upon NA square plus, now what will happen? This PA and PA will get cancelled and it will go to the numerator. So that's why you'll have this term ln of PA1 upon PA naught. So that is ln of PA upon PA naught is equal to 1 by 2 beta 1 A square upon RTN plus into 1 upon NA1 square plus ln of PA1 upon PA naught minus 1 by 2 beta 1 into A square upon RTN into 1 upon NA square. Let us continue with this equation. So previously we got ln of PA upon PA naught is equal to 1 by 2 beta 1 A square upon RTN into 1 upon NA1 square plus ln of PA1 upon PA naught minus 1 by 2 beta 1 A square upon RTN into 1 upon NA square. That is, I will write it in this form. Ln of PA upon PA naught, that is equal to 1 by 2 beta 1 into A square. And now what I have done in this step with the second term. In the second term, I am multiplying with V square and dividing with V square because I want to replace one term in this equation. I'll tell you. So what I have done for the third term in the equation, I have multiplied with V square and divided with V square. What is V? V is volume of Na, moles of gas that occupy the surface of the adsorbent. So Na, since Na is the number of moles of A that are on the surface of the adsorbent, so those moles has a volume of V. So it is ln of PA upon PA naught is equal to 1 by 2 beta 1 A square upon RT 1 Rtn into 1 upon Na square plus ln of Pa1 upon Pa naught minus 1 by 2 into beta 1 A square into V square divided by Rtn Na square into 1 upon V square. So that is ln of Pa upon Pa naught is equal to 1 by 2 beta 1 A square upon Rtn into 1 upon Na1 square plus ln of Pa1 upon Pa naught minus 1 by 2 beta 1 A square upon Rtn. And I wanted this term. So this is V upon Na square into 1 upon V square. Let us move ahead. Let us continue with this equation. So previously we got ln of Pa upon Pa naught is equal to 1 by 2 beta 1 A square upon Rtn 1 upon Na1 square plus ln of Pa1 upon Pa naught minus 1 by 2 beta 1 A square upon Rtn V upon Na square into 1 by V squared. Now in this case Na upon V is moles per unit volume. So that is nothing but molar density. I'm going to denote that by rho A. Rho A is the molar density. So next job is I will replace this term. So it is V upon Na square. So it will be 1 upon rho A square. So you have ln of Pa upon Pa naught is equal to 1 by 2 beta 1 A square upon Rtn into 1 upon Na1 square plus ln of Pa1 upon Pa naught minus 1 by 2 beta 1 A square upon Rt capital N into 1 by rho A square into 1 upon V square. So that is ln of Pa upon Pa naught is equal to 1 by 2 beta 1 A square upon Rtn 1 upon Na1 square plus ln of Pa1 by Pa naught minus 1 by 2 beta 1 A square upon Rtn into 1 upon rho A square into 1 upon V square. Let us continue with this equation. So previously we got ln of Pa upon Pa naught is equal to 1 by 2 beta 1 A square upon Rtn 1 upon Na square Na1 square plus ln of Pa1 upon Pa naught minus 1 by 2 beta 1 A square upon Rtn into 1 upon rho A square into 1 by V square. So this is ln of Pa upon Pa naught. I will write it in this form now. Ln of, if I write it like this, ln of Pa upon Pa naught is equal to L minus M upon V square. And if this is equation 8, and equation 8, L is nothing but this term 1 by 2 beta 1 A square upon Rt capital N 1 into 1 upon Na1 square plus ln of Pa1 upon Pa naught. Whereas M is 1 by 2 beta 1 A square upon Rt capital N into 1 upon rho S square. So equation 8, now let us write it in a proper form. It is written like ln of Pa upon Pa naught is equal to minus M into 1 by V square plus L, and I am calling it as equation number 9. Now we will talk more about equation number 9. So previously we got equation 9 ln of Pa upon Pa naught is equal to minus M into 1 upon V square plus L, equation 9. Now what can you say about equation 9? Equation 9 is called the Harkins-Zura, that is HJ equation, the isotherm. It is called Harkins-Zura HG equation. It is of the form y is equal to mx plus c, equation of a straight line, where capital Y is nothing but this ln of Pa upon Pa naught and capital X is 1 upon V square. The slope is minus M, and you know what is M, and I have just told you what is M, and C is the intercept on the y-axis is capital N. You know what is capital N. So you can simply plot the terms ln of Pa upon Pa naught. It can be plotted on the y-axis, and 1 upon V square can be plotted on the x-axis. You are going to get a straight line but of negative slope, and slope is minus M and the intercept is here. So by knowing slope or intercept, because you have AS in both the terms, so you can find out the area of the adsorbed. So in this way, we have put the Gibbs adsorption isotherm in an appropriate form, in a form which is useful to find the area of adsorb. So this is it. First we got the Gibbs adsorption isotherm, and then we put it, we have put it in a form that is useful. So with this, I end my discussion for the Gibbs adsorption isotherm. I hope you have understood the concept. You have understood the derivation. If you have any doubts, you please mention them in the comment section. So thanks for watching this video. Do subscribe to my channel. Tell your friends to subscribe to it. And if you have any doubts, as I said, you please mention them in the comment section. In my next video, I will be discussing the Freundlich adsorption isotherm, which is applicable to adsorption of liquids. So for now, thank you, and I'm sure you'll be with me in my next video lecture. Thank you. Have a nice day. Bye bye.